ready. So thank you.
So I'm going to talk a little bit about disease-specific allele frequency filtering, and at the end I've got some more slides on variant penetrance depending on how we get on. Everybody feel free to jump in if you have any questions or if I've jumbled the explanation of something and you want me to go through it again. So obviously we're all incredibly familiar with this grid, and what I'm going to talk about relates very much to the top row of this grid. Oh, that wasn't what I was supposed to do. So looking at whether the allele frequency of a variant is compatible with it being involved in disease or not. The disorders that I study are cardiac phenotypes, and so it's also relevant to look at this in terms of PM2 as well, because for these disorders which are late onset, then actually we don't ever expect them, the more frequent the pathogenic mutations to be absent from NOMAD, because we expect 1 in 500 people in that database, for example, to have hypertrophic cardiomyopathy. So this kind of layers into both BS1 and PM2. So we defined last year an approach to creating disease-specific allele frequency thresholds. So rather than taking generic thresholds for any disease, so people used to take kind of 1% for recessive or 0.1% for dominant, we showed that you can drill down a lot rarer than this if you take into account the architecture of disease. So from first principles, a variant cannot actually be more common in the general population than the disease that it causes. But also we know there's more going on than that. We know that there's a huge amount of heterogeneity in the majority of diseases that we study. The majority of us wouldn't be in a job if there was one variant that caused one disease. It would be very easy to find, and we wouldn't need to do all this curation anyway. And so we know that these things are very heterogeneous, and any individual variant only ever causes maybe around 2% of disease. But we also commonly know that particularly for cardiac phenotypes in cancer and these late onset disorders, that variants can be low penetrant, in that not everybody with the variant actually goes on to develop the disease. So with this very simple equation, we can define a maximum credible allele frequency of any disease-causing variant in the general population. Now this is a lot easier to understand if I put some numbers on it. So this is the example of hypertrophic cardiomyopathy. So here we HCM has a disease prevalence in the general population of 1 in 500. So we multiply this by 0.5 because that's because it's a dominant disorder. So that translates to 1 in 1,000 alleles. We looked at a load of examples in the literature, so of all known HCM causing variants, and we couldn't find any that had a lower reported penetrance than 50%. So we used this as our penetrance term. And finally, as heterogeneity, we looked in, we're very fortunate with HCM that we actually have a very large cohort of over 6,000 individuals from clinical testing at the Laboratory of Medicine in Boston and the Oxford Regional Genetics Lab here in the UK, in that we can actually assess in that data set as to what is the most common disease-causing allele. And that is this MYBPC3 missense variant that causes up to 3% of all European HCM. So if we plug these numbers into our equation, we get a maximum credible population allele frequency for HCM of 6 times 10 to the minus 5. Now this is a lot lower, you might realize, than the 0.1% that a lot of people would use for a dominant disorder. So just to kind of show one figure which I hope will convince you that this approach is valid. And here we have an odds ratio on the y-axis of a burden test for MYBPC3 in MY87, and on the x-axis are bins of allele frequency. So here 0.1% are all variants that are more common than 0.1%, and 0.05 translates to those within the bin between 0.05 and 0.1. Wait, that's the other way around. Basically, what I'm trying to show here is that all of the signal of this burden test is confined to this lowest allele frequency bin on the right-hand side, so the only confidence that doesn't overlap 1, and this is corresponding to variants that are rarer than our predefined frequency threshold of 6 times 10 to the minus 5. So James Ware created an app at codb.org/allele frequency app, which helps with calculating these maximum credible allele frequencies. So here there's kind of some sliders, so you can go on and you can put in your prevalence estimate, use the sliders to put in your estimate of heterogeneity and your penetrance term, and it actually calculates for you this maximum AF value. Now there's actually a second step to this approach, and that is because we don't actually know the true population allele frequency of any variant. All we know is what has been observed in the subset of the population that we've subsampled. So at the moment, that is the 140,000 people that are within the NOMAD dataset, for example. So we need to account for this. And secondly, we need to account for the fact that we see in these datasets what we call a considerable left skew. And that is that any variant that is observed as a singleton in the exact dataset, for example, is much more likely to still be observed as a singleton within NOMAD than it is to be observed at a frequency of 1 over 60,000. So we need to take this into account as well. And this is what this figure here that I've taken from the exact paper. So this is showing that same effect in ESP versus exact. So here you can see that the variants that had an allele count of 1 in blue in the ESP dataset are much more likely to still have an allele count of 1 in the NOMAD dataset. So the very left-hand bar, there's this huge blue bar here. So they're much more likely to still be very rare. So we need to account for this sampling variance. So I've still got exact written on here. I haven't updated these slides. So what we can do here is we can calculate, using a Poisson distribution, the maximum allele count that we'd expect to see in a large data set, such as exact and NOMAD. And there is actually another tab. So either the bottom half of the tab that we were on before could calculate AF. If you look on the top of, can you see my pointer? Or can I just only see my pointer?
What was that? Sorry, can we see your...
Can you see my mouse pointer?
Yes, yeah.
Okay, cool. So on this row on the top, so the previous tab I showed you was this calculate AF, but now I've kind of switched to this calculate AC here. And you can input your maximum population allele frequency that we calculated that was disease specific, and the size of your reference population, and the confidence here, and it will tell you how many alleles you can observe in this reference population to actually be compatible with your derived disease specific maximum. However, it's sometimes a little complicated to be calculating Poisson distributions for all of your variants, so we tried to make this a little bit easier by pre-calculating a load of these values. So here on the left is the framework that I showed before, where you, as the user, have defined your disease-specific maximum credible allele frequency. And on the right here, what we have done is we have calculated this filtering allele frequency, which is purely looking at the observed allele counts and allele numbers in exact or NOMAD. So it's not in any way disease-specific. But what this filtering, so this takes into account all the different populations in NOMAD and this sampling bias, and creates a value such that you can directly compare it with your disease-specific maximum credible population allele frequency to decide whether a variant is a credible candidate for disease or not. Now, at this point, I just want to ask if there were any questions. Okay, great. So it's sometimes a little bit conceptually hard to visualize what this filtering allele frequency is. So this sentence in italics here is how we described it in the paper, and it relates to the highest true population allele frequency, where the upper bound of the 95% confidence interval for a Poisson distribution is still less than the variance observed allele count in the reference samples. That's a bit of a mouthful. So instead I'm going to kind of do this graphically. So here we have this red line, which actually equates to the observed allele frequency in NOMAD, where increasing allele frequency is from left to right. And what we do is we just estimate a random allele frequency which is lower than what we observe. And we take the confidence interval around this, shown by these blue lines. And what we do is we sequentially push this estimate further towards this red line and stop where we have the closest we can possibly get to that line without touching or crossing it. And this value here is what is our filtering allele frequency. In other words, it is a lower bound on how common that variant can be. So how we used to filter is if even this allele frequency is greater than our maximum tolerated, then it cannot be a credible candidate to cause disease. Now I hope that makes sense. So these filtering allele frequency values have been on the exact browser for a while. So here you can see that our filtering frequency is 5 × 10⁻⁶, and because we're looking at every individual population, so we're saying that if a variant is too common in any one population, it's too common to cause disease. So here this variant has this filtering allele frequency, and the highest FAF was found in the European data set. So very, very recently, with the release of the new Nomad browser, we now have these numbers also in Nomad. This is calculated separately for both the exomes and the genomes. Unfortunately, we slightly messed this up, and they currently don't have the identifier of that population in there, but I'm going to get that put back in. So basically, what you do here is you can go into, if you were looking at this, this is the famous R502W variant that causes HCM. It's the most common HCM causative variant. And if you look at, so you compare these filtering allele frequencies directly to what we've pre-calculated as our maximum HCM threshold, which was 6 × 10⁻⁵, and you can see that the filtering allele frequency values are lower than this 6 × 10⁻⁵, and therefore we retain this variant as a credible candidate to cause disease. So you can do again this if you go along the tabs in the allele frequency app. You can find this one that says inverse AF, and you can put in your observed population allele count and your allele number, and it will directly calculate this filtering allele frequency value for you. So this is useful if you have a population that is not the Nomad population. So if you have your internal set of controls, for example, you could define a filtering allele frequency. Similarly, with the Calculate AC tab, you could also use that to calculate in your own internal controls how many what the tolerable allele count is. So as I said, we've just put these values into the Nomad browser. We've also got them for any kind of savvy bioinformatics people in the new Nomad VCF as filtered in the info column. And we've now listened to a lot of feedback from people and expanded this data to now include both 95 and 99% confidence. We've included the separate values calculated across all the major ethnicities. And importantly here, we never calculate FAF on the founder population, the Finnish or the Ashkenazi Jewish, or on the small other population. And we now also have, for the non-pseudo-autosomal regions of the X and Y, we have this calculated separately for both males and females. This was through talk with some of the Decipher people at the Sanger, that this is useful for looking at X-linked disorders. So a load of new numbers, basically. And then I just want to flag up some caution. So obviously, there are going to be funny things. So one of the reasons we don't use the Finnish or the Ashkenazi Jewish populations for this is due to founder effects. And there are some variants that are known founders that actually can violate this approach. However, for the most part, because this framework makes the assumption that no newly identified variant will be more common than the most commonly known variant, this is most likely, in the most part, going to be an overestimate, so it should be safe. We also need to be careful for genes that are not well studied or populations that are not well studied. So given that we have, for HCM, for example, these 6,000 individuals that have been sequenced for the whole of MY87, MYBT3, these common genes, we do not expect any newly identified variants within those genes to be more frequent in HCM than this most common identified variant. However, if we suddenly find a new gene, actually, because we've not just discovered it so far, it's not likely to cause a huge portion of disease for HCM, for example, but in other disorders, it might be worth taking this into account. And finally, to calculate these thresholds in the first place, when we calculate our disease-specific maximum tolerated allele frequency, we have to define an architecture in order to calculate that. So, for example, I specified a minimum penetrance of 50%. But actually, if there are alleles that are lower penetrance than that, they might violate this architecture that we've defined. So crucially, we will always retain variants that are within our defined architecture. So I just wanted to flag that we also have a recessive model for this, and on the allele frequency app, there is a second slider for genetic heterogeneity as well as allelic heterogeneity, and that relates to this recessive model. Where as well as looking at the maximum frequency of any disease-causing variant, we look at this separately between what proportion of disease what's the maximum proportion of disease any gene could contribute, and within that, what's the maximum any allele could contribute. So this takes into account that compound heterozygotes can only be formed within variants for two variants within the same gene and not for two variants in separate genes. So a question that I kind of commonly get asked is, well, great, you have these 6,000 individuals. That means for HCM you've managed to define this quite nice figure for heterogeneity, and this is actually a lot more difficult for other disorders. So how else can we estimate heterogeneity? So this first approach here is what we did here, and we looked for the most common disease-causing mutation in a large case cohort, but we obviously don't always have these. And so one thing we can do is we can look across similar disorders, or if we're really unsure, we can actually often make an estimate of what is the maximum proportion of disease that's attributable to any single gene if we can't drill down to an individual variant. And if we're really unsure, we can actually say, well, we can assume all of the disease is attributable to a single mutation, rather than factoring in the heterogeneity as an overestimate. Okay, so I've kind of come to the end of explaining the framework. So does anybody have any questions around any of that?
I do have a question, Nikki. This is probably a really basic thing, but you said that the filtering allele frequencies are available at 95% and 99% confidence levels. So what are the pros and cons of using one versus the other? I would have thought that 99% would be what you want to use, but I'm just kind of curious as to the difference and when you might want to use one over the other.
So we have always just used 95%, and that's what's displayed in the browser. That's what the only values we released for exec.
Okay.
And so that's kind of our recommendation, and that's because there was already a lot of kind of caution built into this approach. The 99% is there because some people said to us, well, actually, I want to be stricter than that. I want to be even more conservative, so I would like a 99% value. So we added those in. But we don't expect to actually use them ourselves.
Okay. All right. Thank you.
Hi. I have a question as well. One of the questions that came up in one of our expert panels was the prevalence that we typically find in the literature is highly ascertained, and so we don't really have a population-based prevalence. Do you think this already sort of takes that into account? I know you have also a calculator for population-based prevalence as well. Do you recommend that we use that? So
the prevalence estimates, it's an incredibly tricky question, and we've always just gone for what is the most prevalence ever been reported as, and that will be a conservative estimate. So you'll then always overestimate the maximum credible allele frequency, and you won't be removing anything that you don't want to. So that's always been our approach. In terms of actually defining prevalence for diseases, that's not something I can give a huge amount of advice on, I don't think.
Thank you.
Okay. I have no way of telling what time it is with my screen taken over with this presentation, by the way. So somebody might have to keep me slightly informed of it.
It's 24 minutes past the hour right now, Nikki.
Okay, that was very exact. Thank you. So I'm just going to kind of take this in a different direction for a minute. This is some kind of cool data that we've found looking at this approach. So this is kind of going into investigating penetrance a bit more. So this plot here is showing the count of HCM variants that are classified as VUS, light pathogenic, or pathogenic in these over 6,000 HCM cases that I mentioned earlier. And that count of cases is on the x-axis, and up the y-axis we have this filtering allele frequency. And this and these variants are coloured by the pathogenicity. And this kind of black line and the surrounding grey section is indicating where the count in cases and the allele frequency in nomad are roughly equivalent. And this blue line across the bottom is this HCM, the threshold that we calculated earlier of 6 times 10 to the minus 5. And the little plot here is the zoomed out version, and the bigger plot is actually the bottom left-hand corner. And as you can see from this, basically, is that the known pathogenic variants that are red tend to lie along the x-axis and actually are incredibly rare in controls and nowhere near our HCM threshold line. But there are a couple of variants that pop out and look really funny compared to the rest of the distribution. And the question here was, well, what are these variants? Particularly there's one here that's obviously been identified as pathogenic. So we thought, okay, let's have a look at what the penetrance of these variants are. So we're using this equation that Eric Nicola suggested in his paper on prion disease, where we purely look at the case and control allele frequencies and the known prevalence of the disease to calculate the penetrance using this equation. Again, going back to the allele frequency app, there is another tab called penetrance, which will let you use this equation by plugging in your own numbers here. So this is the first of those two variants. So this is the variant that was flagged as pathogenic. And if you look in the ClinVar data, it seems that is clearly the case. It segregates with disease in multiple families. There's actually functional data to show that it causes skipping less than 30, but it has been actually reported as incomplete penetrance. If we look at the data in nomad, it actually seems to be an African-specific variant. So if we drill our cases down to just those that we know are African, firstly, we can see that this variant in Africans seems to be more prevalent than our most common HCM variant. And secondly, you can see that when we calculate our penetrance, the penetrance estimate is 12%. And that even the upper confidence of this penetrance estimate is lower than the 50% that we accounted for in our disease architecture, suggesting that this variant is low penetrance. The second of those variants was identified as the VUS. If you look in ClinVar, there is very weak segregation data, and also it has been identified in trans with a known pathogenic MYBC3 variant, and actually in that circumstance it was shown to lead to severe and early onset disease. So this variant is European specific. So again, if we just drill down to the cases that we know have European ancestry, we see this variant is very low penetrance estimate. And given the co-occurrence with this MYBC3 variant in ClinVar, it suggests that this might actually be a modifier variant. So we then expanded this analysis to other cardiac disorders. And the main reason for this, to be completely honest, is the fact that some people including some researchers from Human Longevity Inc. and Craig Venter, published a paper looking at the overrepresentation of mutations in ClinVar above disease prevalence estimates. And in that, they filtered variants with their own frequency filtering approach. And in that paper, they actually said that our method was prone to removing pathogenic variants, which is not correct. So we wrote a response letter to that paper, which is now on bioRxiv. But in doing so, we actually did a wider analysis on penetrance in cardiac conditions. So here we've taken 5 of the more common cardiac conditions: dilated, hypertrophic, and cardiomyopathy, ARVC, Lonsdale syndrome, and Brugada syndrome. And there were 58 lycopathogenic or pathogenic variants in ClinVar that actually are above our calculated disease-specific thresholds for each of these diseases. And this table, you can see these broken down by the approximate ClinVar star status. So the 2-star ones being ones that have multiple submitters that have given their criteria. 1-star being this is only a single submitter, but they have provided criteria, and other being the ones where they're mainly literature only, OMIM, that kind of stuff. There's no real evidence behind them. And as you can see, all of the 1-star and the other variants here So what we did with these 58 variants is we took them and we manually classified them to ACMG, and the majority of them, so 82%, and all of the ones that are 1-star or other, there was no evidence to call them pathogenic or like pathogenic in our hands. And of the 2-star ones, there are actually 8 interesting variants that actually do occur more frequently than our maximum calculated threshold. Looking into these, one of these is actually the 8CM variant that we visited earlier, the one that was the red dot that stuck out on the plot. 2 of them are Brugada syndrome, and the vast majority of them are long QT. And we know that variants of long QT are often low penetrance. And particularly, a couple of these variants recapitulate a known low penetrance mechanism in long QT, in that in homozygous form, these variants cause dual Lange-Nielsen syndrome, but in heterozygous form, no low penetrance in the carrier relative. So crucially, for these 8 variants, when we calculated the penetrance of them, they were all well below, including the upper confidence interval, well below the 50% threshold that we defined within our architecture. So crucially, this approach works perfectly well within the architecture that we define. And it's worth flagging here that even these variants, if they have evidence towards pathogenicity, by ACMG would never actually be classified as likely benign or benign anyway. So using these frequency thresholds for BS1 is perfectly safe. So that is all I have to say. So hopefully I've convinced you that we have a statistically robust method to disease-specific allele frequency filtering, and that this enriches for disease-causing variants and is safe to use in the context of the ACMG guidelines. Go and visit the allele frequency app and have a play with all the different tabs. There's lots of cool stuff in there. We have very recently released the new filtering allele frequency values for Nomad, and with that comes loads of new features. I'm actually going to write a blog post on this, hopefully over the next week or so, for some more background. And then just for the slides on the end, I just wanted to talk a little bit about how we can use this framework to study actually the architecture of disease, find a low penetrance modifier variants. And in cardiomyopathy, at least, these don't seem to be that common, these very low penetrance variants. And yeah, using this approach, we can actually recapitulate known mechanisms of low penetrance with long QT. And with that, I'm done. Any questions?
I have one more question. So there's 2 codes for the ACMG. One is supporting, at least towards pathogenic, so the BS1 and then the BA1, which is the standalone. How do you how do you guys approach differentiating between the 2 using this method?
So the method in the form that we created it, where we drill down fully to heterogeneity, we use for BS1. But it does obviously make sense to use this in some form also for BA1, the standalone criteria. But in that sense, it might be as simple as saying this is equivalent to the the prevalence of the disorder, rather than drilling outside with heterogeneity. And I know I've forgotten exactly how all of the different groups have done it. Does that answer your question?
So just to clarify, for BA1, you would set heterogeneity to 100 or 1, and then the...
So that would be the conservative approach to doing it. You can also lower the penetrance. So you could say, if we say minimum penetrance of 30% and only a single disease-causing variant, that would be an incredibly conservative value to have as BA1.
Gotcha.
So any other questions for Nikki?
Yeah, I have a question. So, thanks for your talk, Dr. Whiffen. The filtering frequencies on Nomad, are they're specific per gene? Is that correct?
So the ones on Nomad are specific per variant.
Per variant.
So
okay.
all that takes into account is the observed allele count and the observed allele number in each individual population within Nomad. So they're of variant attributes.